Hello everyone, welcome to my Rashid channel. In this video, I will explain you how to calculate the size of distribution board that we call DB and some main distribution board that we call SMDB, main distribution board we call MDB, transformer size and cable size for multi-story residential building. I will explain step by step with proper formulas so that you can understand and apply this knowledge in real projects. We have a multi-story residential building. The building has ground plus 5 floor, means total 6 floor. Each floor has 3 units of 3 BHK flats and 3 units of 2 BHK flats. To calculate the electrical load, we will consider a standard power rating for different type of appliances used in 3 BHK and 2 BHK flat. So each 3 BHK flat contain various electrical appliances, each consuming a certain amount of power. Let me write here. Lighting and fan I consider 2 kilowatt. Socket 1.5 kilowatt. Kitchen appliances 2 kilowatt. AC unit we consider 2 numbers, that is 4 kilowatt. Geyser same 2 numbers, 4 kilowatt. Miscellaneous load 1.5 kilowatt. So the total load of 3 BHK flat will be 2 plus, I need to calculate this all value. It becomes 15 kilowatt. Now we will consider demand factor. Why we use demand factor? Because all electrical appliances and equipment will not operate at the same time or at a full capacity. If we design based on the total connected load, it will be overestimation, leading to unnecessarily large equipment and higher cost. So as you can see here, in this 3 BHK flat, the total connected load is 15 kilowatt. But we will apply here demand factor 0.7 because not all appliances will run together. So the actual demand load will be 15 kilowatt multiplied by 0.7 equal to 10.5 kilowatt, making the system more efficient and cost effective. So for 2 BHK flat, let's consider lighting and fan is 1.5 kilowatt, socket 1 kilowatt, kitchen appliances 2 kilowatt. I consider geyser here, one number, that is 2 kilowatt. Miscellaneous load 0.5 kilowatt. Then the total load will be, calculation of this all load, equal to 7 kilowatt. Same way we will add here demand factor 0.7. After adding the demand factor, we get demand load equal to 7 multiplied by 0.7 equal to 4.9 kilowatt. Since each floor contains 3 units of 3 BHK and 3 units of 2 BHK flats, so the total 3 BHK load per floor equal to 3 multiplied by 10.5 kilowatt equal to 31.5 kilowatt. Same way, total 2 BHK load per floor equal to 3 multiplied by 4.9. This 4.9 is a single unit of 2 BHK flat, and we have a 3 numbers of 2 BHK flat in each floor. So the 3 multiplied by 4.9 kilowatt equal to 14.7 kilowatt. Now the total load per floor, we will add this both value, 31.5 kilowatt plus 14.7 kilowatt equal to 46.2 kilowatt. Now we need to calculate total flat load from ground floor to 6th floor. So each floor load has 46.2 kilowatt multiplied by 6 equal to 277.2 kilowatt. Now we will consider common utility load like lift, pump, lighting, etc. So I considered 50 kilowatt. Let me consider demand factor for common utility load is 0.8. Because for common utility we usually consider 0.8 or 0.9, sometimes 1. So it depends on your standard. I consider 0.8. So the demand load for common utility is 50 multiplied by 0.8 equal to 40 kilowatt. Now we will calculate the total demand load of all building. We already calculated for flats, that is 277.2 kilowatt plus 40 kilowatt what we calculated here equal to 317.2 kilowatt. This is the total demand load. So once we calculate the total load of the building, then we can find easily transformer size. To choose the right transformer for the building, it need to handle the total demand load, which is 317.2 kilowatt. So the building demand load 317.2 kilowatt. I need to convert this kilowatt rating into kVA rating. That is why we need power factor. Let's consider power factor 0.8. After divide by power factor, we get equal to 396.5 kVA. So this is the total load, 396.5 kVA. Now we add 20% extra margin for future growth and safety. After adding 20%, that is 396.5 multiplied by 1.2, this is the 20%, equal to 475.8 kVA. This size of transformer is not available in the market. So we will choose the next bigger size of transformer, which is 500 kVA. We can select here 500 kVA transformer. Now we need to calculate distribution board, that is DB, for each flats, means 3 BHK and 2 BHK flat. So let me consider first 3 BHK flat DB size. As we calculated, the total load of 3 BHK flat is 10.5 kilowatt. Since this load is greater than 7 kilowatt, so we can use here 3-phase DB. We will install 3-phase DB because the load is more than 7 kilowatt. So for the main breaker calculation, first I need to calculate current for the flat. As we know the formula, current equal to power multiplied by 1000 because this is in kilowatt divided by root 3 multiplied by voltage multiplied by cos phi. So let's substitute the value. Power we have 10.5 multiplied by 1000, this is kilowatt, divided by 1.732 multiply 415 multiply 0.8, this is a power factor what we considered. So the current value will be 18.26 ampere. Now we will add 25% safety factor. So after adding 25% of safety factor in the current, that is 18.26 ampere multiplied by 1.25 equal to 22.82 ampere. 22.82 ampere size of MCB is not available. So we will choose the next standard size of MCB which is available in the market is 32 ampere. And because we are using 3-phase DB here, so we will choose 32 ampere TPN MCB. This is 3-pole neutral MCB. So the main incoming breaker will be 32 ampere TPN MCB. You can also choose a 25 ampere MCB if it is available in your market. In my case, I am using 32 ampere MCB. However, this small difference in MCB rating will not significantly impact the overall selection of the system. Now for outgoing MCB, we can select based on appliances load. I am not calculating the load for each outgoing circuit because this video will be so long. But for your understanding, I considered 5 numbers of 10 ampere MCB for lighting load, 3 MCB for 3-bedroom, 1 MCB for drawing room and 1 for kitchen, total 5. 5 numbers we use for lighting load. Same way, for socket, I considered 5 numbers of 16 ampere MCB, like a 3-bedroom, 1 for drawing and 1 for kitchen. Now AC, we have 2 AC in 3 BHK flat, so we will install 2 numbers of 16 ampere MCB, or you can install 20 or 25 ampere based on your AC load. So I considered 2 numbers of 16 ampere MCB. For geyser, we have 2 numbers of geyser. I consider 2 numbers of 16 ampere MCB. Kitchen appliances, I consider 1 numbers of 16 ampere MCB. So the total outgoing MCB will be 5 plus 5 plus 2 plus 2 plus 1 equal to 15 numbers. 15 numbers of MCB we required in this DB. Since we are using 3-phase power supply, so we required 3-phase DB as well. So for 3-phase DB, we need to distribute MCB for each phase. So the load per phase equal to 15 divided by 3 equal to 5 numbers. We need 5 numbers of MCB in each phase. Let me keep 1 extra MCB for each phase, so it becomes 6 number. So here we can use 6-way TPN DB As you can see here in this drawing I just made for you, the dBs look like this. Now let's calculate for 2 BHK dB. The total load of 2 BHK flat is 4.9 as we calculated. So for 4.9 we can use here single phase dB, because single phase dB is enough and the load is very less than 7 kilowatt, or less than, we can say less than 5 kilowatt. So in that case we can use single phase dB, that is SPN dB. So let me calculate current first. Current equal to P multiplied by 1000 divided by V cos phi. This is a single phase formula. 4.9 multiplied by 1000 divided by 230, because the single phase is 230, multiplied by 0.8. The total current is 26.63 ampere. Let me add 25%. This is for safety factor. Current will be 26.63 ampere multiplied by 1.25 equal to 33.28 ampere. So the next standard size is 40 ampere SPN MCB. This is single phase neutral MCB. So this is the main incomer of 2 BHK flat dB. Let me calculate outgoing MCB for you. Lighting, I consider 3 numbers of 10 ampere MCB because we have a 2 BHK flat, 2 for 2 bedroom and 1 for common and kitchen. Socket 3 numbers of 16 ampere MCB. Geyser 1 number of 16 ampere MCB. Kitchen appliances 1 number of 16 ampere MCB. So the total outgoing MCB will be 3 plus 3 plus 1 equal to 8 numbers. I will keep 2 numbers pair. So we can use here 10-way SPN dB, as you can see here in this drawing. So this is the size of dB but we use for 2 BHK flat. Now it's time to calculate SMDB. This is called sub-main distribution board. Each floor has 6 flats with a total load of 46.2 kilowatt. This is the demand load. Now we will calculate sub-main distribution board size for each floor. So the voltage is 415. Power factor we considered 0.8. Now we calculate the current rating. Current equal to 46.2. This is the power multiplied by 1000 divided by 1.732. This is the √3 value multiplied by 415 multiplied by 0.8 equal to 80.4 ampere. This is the total current of each floor of the flat. So let me add 25% of safety factor. So the safety current will be 80.4 ampere multiplied by 1.25 equal to 100.5 ampere. So we can select next standard size of main breaker, means MCCB, equal to 125 ampere, and this is TP, 3 pole only. We will use here 3 pole 125 ampere MCCB, because this is a SMDB sub-main distribution board, so we will use MCCB for incoming and outgoing both. Since the 3 BHK flat has load of 10.5 kilowatt and we have 3 flats, we need to provide protection for 3 unit of 3 BHK flat. So in that case we need to select 32 ampere TP MCCB for each flat. Now for 2 BHK flat, each 2 BHK flat has total load 4.9 kilowatt and we have 3 flats. So we can select 40 ampere SP MCCB, that is single phase MCCB, for each 2 BHK flat. So we required here 3 numbers of 40 ampere SP MCCB for 3 numbers of 2 BHK flat. I think you have noticed I have selected same rating of MCCB which we install in each dB incomer in the flat. You can see here. We use TP MCCB in the SMDB outgoing circuit because MCCB has a high short circuit current like 25 kiloampere, which is useful for protecting the system against high fault current. This is important because the SMDB handle a larger load and we need more protection in case of short circuit. Now if we talk about inside the individual dB, Here we use TP and MCB for protection. Actually, MCB has lower short circuit rating, around 10 kiloampere. So they will trip first in case of short circuit before the MCCB. You can also select a one size higher rating of MCCB in the SMDB outgoing circuit compared to MCB in the TB incomer. Let's calculate the incoming power cable size from the main distribution board to SMDB 5, which is located on the 5th floor. This process will be similar for all the other SMDBs as well. So for cable calculation, we need to check the incomer MCCB rating. So first we will look the incomer MCCB rating inside SMDB, which is 125 ampere. We already calculated above 125 ampere. This is the SMDB incomer rating. Based on this current rating, we can calculate the derating factor. Let's assume the total derating factor is 0.8. For a more accurate derating factor, you can refer to the cable catalog, which provide values based on your specific cable laying pattern and ambient temperature. Anyway, I have assumed 0.8 derating factor. Then the continuous current rating of cable will be 125 divided by 0.8 equal to 156 ampere. So the cable we will choose must have higher current rating capacity than 156 ampere. So let me refer to the cable catalog. Here in this page, 4-core copper cable this. Yeah, here we can see 4-core copper XLPE cable. The current carrying capacity of this 4-core 70 mm square cable is 180 ampere. Actually, we have to lay this cable inside the duct. So this size of cable is sufficient for the continuous current rating of 156 ampere. But before finalize this cable, we need to check voltage drop as well. We need to ensure that voltage drop of the cable does not exceed 3% of system voltage. Since our system voltage is 415 volt, then the maximum allowable voltage drop is 0.03, this is 3% multiplied by 415 equal to 12.45 volt. So this is the maximum allowable voltage drop. Now we need to choose a cable that ensure the voltage drop is less than 12.45 volt. Here voltage drop formula is root 3 multiplied by current multiplied by cable resistance multiplied by length in kilometer. We can get cable resistance from cable catalog. So let me open catalog again. And here we can see the cable we selected 4-core 70 square mm 0.3430 ohm per kilometer. So let's substitute this value into the formula. Root 3 multiplied by 125. This is full load current of SMDB. Multiplied by 0.3430. This is the cable resistance. Multiply. Let me assume the distance from MDB to SMDB is 50 meter. So I need to convert into kilometer. Then it becomes 0.05. This is in kilometer. So after solving this equation, we get 3.71 volt, which is much lower than 12.4 volt limit. So the cable is perfectly fine. Therefore, we can select this 4-core 70 square mm copper XLPE cable from the MDB to SMDB 5. Now let's size the SMDB for common utilities. For common utilities, the total demand load for common utilities is considered to be 40 kilowatt. To calculate the current, we use the formula current equal to 40 multiplied by 1000 divided by 1.732 multiplied by 415 multiplied by 0.8. Then equal to 69.5 ampere. Now let's apply 25% safety factor. So 69.5 multiplied by 1.25 equal to 87 ampere. We required MCB, which is rating 87 ampere, but it is not available in the market. This is not a standard size. So we can choose MCCB which is available in the market is 100 ampere TP. This is the next standard size. Now we will calculate MDB size, that is main distribution board, which is feeding to all SMDBs in the building. We have already calculated total building load, that is 317.2 kilowatt. Then we need to calculate current. I equal to 317.2 multiplied by 1000 divided by 1.732, 415 and 0.8. It become 551.6 ampere. So the total ampere rating of the building load is 551.6 ampere. To ensure safety and accommodate future expansion, we add 20% spare capacity. So the final current will be 551.6 ampere multiplied by 1.2. This is 20%, equal to 662 ampere. To ensure safety and reliability, we will consider next bigger size of air circuit breaker, and it is 800 ampere. We will install here 800 ampere ACB. You can see here in this image, this is 800 ampere ACB. To ensure proper selectivity, we need to make sure that if an overload occurs, the SMDB breaker trip first before the outgoing MDB breaker. To achieve this, we size the MDB outgoing breaker slightly higher than SMDB incomer. Here you can see I have installed 150 ampere outgoing breaker which is feeding to SMDB, and for the common utilities we installed 125 ampere MCCB. Since we have installed 125 ampere incomer breaker in each SMDB, that is why we selected a 150 ampere breaker in the MDB to feed each SMDB. Now let's calculate the cable sizing from transformer to main distribution board. The total distance from the transformer to MDB is 100 meter. First we need to find the full load current of the transformer, because outgoing load is feed through this cable. Using this formula, I equal to 500 multiplied by 1000 divided by 1.732 multiplied 415 equal to 696 ampere. This is the full load current of transformer, 696 ampere. Let me assume total derating factor 0.8. Then the continuous current rating of cable will be 696 divided by derating factor 0.8 equal to 870 ampere. Now we need to find cable which current carrying capacity is more than 870 ampere. So let's refer to cable catalog to find suitable size of cable. We are looking here for core copper cable, XLP type insulation. Looking at the catalog, we can see that the largest available cable size is 4 core 300 square mm, which has current carrying capacity is only 490 ampere. You can see here 490 ampere. This is the current carrying capacity of 4 core 300 mm square cable. But we need a cable capable of carrying at least 870 ampere. So in this case, we will do one thing. If we install 2 run of 4 core 300 square mm cable, then the total capacity will be 490 ampere. This is the capacity of 4 core 300 mm square of cable. Multiply by 2, then it becomes 980 ampere. Means if we will install 2 run, means 2 cable of 4 core 300 mm square, then its current carrying capacity will be 980 ampere, and this is sufficient for our load. But before finalizing, we must check the voltage drop to ensure it is within acceptable limit or not. So for the voltage drop, we have to keep the voltage drop within 3%, which is the common standard for distribution circuit. Maximum voltage drop is 3%, so we can calculate 3% of 415 volt equal to 12.45 volt. Now let's apply voltage drop formula. Voltage drop formula equal to root 3 multiplied by current multiplied by cable resistance multiplied by length. Here you can see resistance of 300 square mm cable is 0.0810 ohm per kilometer. Since we are installing 2 run of 300 square mm cable, the effective resistance will be half. That is, resistance of 2 run of cable equal to 0.0810 divided by 2 equal to 0.0405 ohm per kilometer. This is the total resistance if we install 2 run of cable. Now we can substitute all the value in voltage drop formula. Voltage drop V equal to 1.732 multiplied by 696 multiplied by 0.0405 multiplied by 0.10. This is the distance in kilometer. After solving this, we get 4.88 volt. This is the voltage drop. The voltage drop is 4.88 volt, which is less than 12.45 volt, means less than 3% of system voltage. Therefore, it is acceptable. So the final cable selection will be, after checking both current carrying capacity and voltage drop, our final cable selection is 2 run of 4 core 300 square mm copper XLPE cable. Its total current capacity is 980 ampere, which is greater than 870 ampere requirement. Based on our complete building load calculation, I have created a block single line diagram. This is a 500 kVA transformer. We have used 2 run of 4 core 300 square mm cable as per our calculation. This is the main distribution board, MDB. From the MDB, 7 SMDB are connected. With each SMDB fed by 4 core 70 square mm cable. The SMDB are distributed as follow: 1 SMDB for the ground floor, 1 for common load, 1 each for first floor, second floor, and so on. From each SMDB, multiple flats dB are connected, like 3 numbers of 3 BHK dBs represented in brown as TPNDB, 3 numbers of 2 BHK dB represented in black color as SPNDB. The common utility SMDB supplies power to lift dB, motor dB, lighting dB, etc. Similarly, all SMDB are connected to the representative flat dBs. This structure ensures a clear and efficient power distribution throughout the building. So guys, hope you understand all this designing. If you like this video, please do like and subscribe my Rashid Iqbal channel. See you in the next video.